In Unit 3A, you started working with quadratic equations, meaning everything here is going to have a highest exponent of 2. We talked about different methods of solve by factoring as well as quadratic formula, and so that's really what we're going to highlight here. First off, anytime you have a quadratic equation of any sort, you need it set equal to 0. So the second example, that's already taken care of, but in this first one, I'm going to need to add that x over. Remember that I typically recommend that you keep your x squared positive, so whatever that means for your problem, that's what I would do. Both of these I picked because they specifically just have two terms, an x squared and an x in this one, an x and a number in the other one. Anytime you have two terms, you really are looking at two primary options. One is that you will be able to GCF. The other is that it is a difference of squares. So I picked one of each of these so I could talk about them. On this first one, you definitely have a GCF because both of them have an x. So I'm going to take an x out, and then I'm going to be left with x plus 1. Then this is fully factored. There's no more squared terms. So I'm going to set each factor equal to 0. And you get your two answers of 0 and -1. Remember, whatever your highest exponent is how many answers you should have. So this was a squared, and I got two answers, which is good. On this second one, again, it's already set equal to 0, so I'm going to try to factor it. There is not a GCF here, but these are both perfect squares, and so this is that difference of squares pattern that we have talked about quite a bit as we've gone throughout the year. Your a value would be the square root of 4x squared, which is 2x. Your b value would be the square root of 9, which is 3. So when I fill this into my pattern, it's going to be 2x plus 3 and a 2x minus 3. Remember that your order does not matter here. And then I'm still going to apply that zero product property, which says that the only way this is true, you have two numbers multiplied to equal 0, is if one of them 0 or if the other one's 0. And then we're going to solve. This one gives me -3 over 2. This one gives me +3 over 2. You can also tell me 1.5 and -1.5. Either is fine. These types we've done quite a bit throughout the year, so I'm not going to do as many of them as I will do other days, but I do want to hit some important parts just to remind you and give you that refresher should you need it. So again, first off, you want it set equal to 0, so I'm going to add this 16 over to the other side. It is important, it is in order. So I need the 16 to be last because it is my constant, my thing without a variable. And then I am multiplying to 16 and adding to -10, which would be -8 and -2. What we did with these always then was we replaced our -10 n term, so n squared minus 8n minus 2n plus 16. And then we draw that line down the middle and factor by grouping. So from the front, you can pull out an n. From the back, you can pull out a -2, and then you rewrite it of the stuff you factored out and the stuff left behind. Then you're going to go ahead and set them equal to 0, and you should get 2 and 8. On this other one, same idea. I'm going to keep my 9k squared positive, so I'm actually going to move both of these things over here. So I have 9k squared plus 3k minus 2, again going in descending exponent value order so that I am in the correct order for my factoring. If it's in the wrong order, you're not going to be able to do it. Here I have a number in front, so I need to make sure to multiply by the back. So 9 times -2 is -18, and it needs to add to 3. Then, let's see, that's going to be 6 and 3, and it needs to be a -3 because 6 minus 3 gives me +3. And again, these terms are going to replace my middle term. So I have 9k squared plus 6k minus 3k minus 2. The order does not matter. It'll work either way. When we draw that line down the middle, from the first two, I can pull out a 3k, and that gives me 3k plus 2. From the back, I can't pull out anything except for a -1 because I need to switch those signs. And then again, we pull one factor is the stuff that I factored out. The other is the stuff that we left behind. Then I set them each equal to 0. 3k minus 1 equals 0. Gives me k equals 1/3. 3k plus 2 equals 0. Gives me k equals -2/3. 2/3, and those are your two answers. You do both of these the same way. Just be careful as you go through. Sometimes, as some of you have noticed, the numbers at the end match, and other times they don't. So I would always be careful, write out the whole problem and go all the way through. Some of us are skipping past that sometimes, and I just want to make sure we're doing it correctly. Okay, this one looks the same way, so I'm going to set it equal to 0. Again, put it in order. So we'll have 10b squared plus 11b minus 3 equals 0. And then I try to factor. So negative 30, doing 10 times negative 3, and adding to 11. You may say that 6 and 5 can do that, but notice your sign, 6 times 5 does not give me negative 30. And even if I made them both negative, that won't work. If I make one of them negative, it doesn't get me to 11. So this is not factorable. And we have reached the point then in this example where we have to figure out what else to do. And in this chapter, you didn't just get to stop if it wasn't factorable. You had to use the quadratic formula. So I'm going to write it out again, and then we'll talk through how to do this, because some of us haven't done it since this chapter. So when we go to do this, your A term is whatever's with your squared term, your B is whatever's with your linear term, or your thing without an exponent, and your C is your constant. And we're going to plug all of this in. So if it says negative B, it's going to be negative 11 plus or minus 11 squared minus 4 times 10, my A, times negative 3, all over 2 times 10. I always start in my radical, so I'm going to do 11 squared minus 4 times 10 times negative 3. That negative 4 times negative 3 means this problem's going to end up being addition. And under my radical, I get square root of 241. What you should always do is take this square root and try to see if anything goes into it, your perfect squares. So that's where we're dividing in 4 and 9 and 16 and so on. With this example, nothing does go into it, so I can't simplify any further, and this would be my answer. That is your two answers because it has the plus or minus. You are welcome to pull it into two different problems if that makes it easier for you. And the answers on your Pear Deck will show you it as two different problems, but you can also write it just as one. We're going to do one more like that. As always, you are welcome to give it a try first and then listen to the explanation. We need it set equal to 0, so I'm going to move everything to do with my x squared. So 6x squared plus 12x plus 9 equals 0. Remember that order does matter. In one like this, I do notice I have a GCF, which you are welcome to take out if it'll make your problem a little bit easier. It shrinks my numbers down, but you don't have to take it out if you don't want to. And you could do this problem either way. This one, if I'm multiplying to 6 and adding to 6, going from that step, nothing's going to work, so I am going to have to factor it. So I'm going to start plugging everything in. Let's see, 6 squared minus 4 times 2 times 3, all over 2 times 2. Again, I'm really just ignoring this 3. Doing the number in the radical, I get negative 6 plus or minus the square root of 12 all over 4. But then I do have to keep going and I need to simplify. 12 is really 4 times 3. And if you remember, square root of 4 is 2, so it's really 2 root 3. So I'm going to rewrite this as negative 6 plus or minus 2 root 3. And each of those is over 4. Usually when I simplify, I find this makes it a little bit easier for people because you have to make sure you simplify both pieces. 6 over 4 does simplify. That's negative 3 over 2. Plus or minus 2 over 4 also simplifies, so it's square root of 3 over 2. You could write this just as one fraction since the denominators match. So either way of writing this one is perfectly fine, but those would be your final answers. Again, if you didn't GCF at first, it will still work. Your numbers are probably just larger right here, but it should eventually simplify down to give you